Passive devices are electronic components like resistors, inductors, transformers, and capacitors. They do not alter the waveform of an alternating current applied to them and hence cannot be used to amplify or rectify currents. Active devices are vacuum tubes, semiconductor diodes, and transistors, or a combination of active devices and passive devices like integrated circuits. They can change the waveform of an alternating current applied to them and hence can be used for amplification and rectification. Rectification is the process of converting alternating current to direct current flowing only in one direction, while alternating currents change direction with a periodicity. Resistors are passive electronic devices which resist the flow of currents through them. Resistance is measured in ohms and sometimes mentioned in higher units like kilo ohms, meaning 1000 ohms, and mega ohms, meaning 1 million ohms. Resistors can be used to limit current in a circuit, as while using a resistor to avoid excessive flow of current through a light emitting diode or LED. They can also be used to provide a voltage using a voltage divider circuit of 2 or more resistors, as in case of providing a bias for the base terminal of a transistor. Transistors are semiconductor devices with base emitter and collector terminals widely used in electronic circuits. Two important types of resistors are wire-wound resistors and carbon resistors. The resistors illustrated earlier are carbon film resistors, the resistance value of which depend on the amount of carbon present in them. Wire-wound resistors can be made of nichrome wire and usually have higher power rating. Variable wire-wound resistors have been conventionally used in rheostats, which are variable resistors with a sliding contact. Variable resistors are also called potentiometers. They have 3 terminals unlike the usual resistors which have only 2 terminals. Central terminal provides the variable resistance with respect to the other terminals. Potentiometers can have a turning knob to alter the resistance value in the circuit and are widely used as volume controls in radios and amplifiers. A preset potentiometer is one in which the resistance value can be changed using a screw-like mechanism and set at the value until it is altered later if needed. Power dissipation capacity of the resistor usually depends on its physical size and can be rated at 0.25 watt, 0.5 watt, 1 watt, etc. Now I am demonstrating the change of resistance, continuous change, as the potentiometer screw is being turned. Just like tuning a radio. The value of the resistor is indicated on the resistor with a color code. The resistors shown here have a 4-band color code, which is the most common one in use. First 2 bands indicate the resistance value, which has to be multiplied by the code on the 3rd band. 4th band indicates the tolerance. All the resistors shown here have a golden band for the tolerance, indicating 5% variation above or below the coded value. If there is no tolerance band, the tolerance is presumed to be 20%. Color code values are as follows: black 0, brown 1, red 2, orange 3, yellow 4, green 5, blue 6, violet 7, grey 8, white 9. Golden color is for 5% tolerance, while silver color is for 10% tolerance. As mentioned above, if there is no tolerance band, it implies 20% tolerance. third band is used as a multiplier for the first two bands. Multiplication is by 10 to the power of the third band color code. Multiply by 1 if it is black, by 10 if it is brown, and by 100 if it is red, etc. This is a symbol of a resistor used in circuits and indicated by the letter R. Resistors can be connected in parallel or series. When the resistors are connected in series, the total value is the sum of the individual values. When they are connected in parallel, it is a complex calculation as shown here. Checking the total value of resistors connected in series is rather simple. You just have to add the total values of each resistor and you get the final value. But it is not that simple when you connect resistors in parallel. You have to take the inverse value of each resistor, sum them up, and finally get the inverse of the sum to get the final value of resistors connected in parallel. To simplify things in the demo, we will take three 10K resistors. 10K resistor has a brown band in the beginning representing a color code of 1, followed by a black band representing 0, and then an orange band representing the multiplier of 1000 or 10 to the power of 3. So the value will be 10 into 1000 is equal to 10,000 or 10 kilo ohms. Single 10K resistor on breadboard measures 9.82K with golden tolerance band of 5%. Selector at 20K position. Three 10K resistors on breadboard measures 29.6K with golden tolerance band of 5%. Selector at 200K position. Two 10K resistors in parallel on breadboard measures 4.91K, about half, with golden tolerance band of 5%. Selector at 20K position. Three 10K resistors on breadboard in parallel measures 3.2K, about 1/3, with golden tolerance band of 5%. Selector at 20K position. Same value of resistors were used for simplifying the calculations so that it is easy to check by mental calculation. If different values are used, it will be more difficult to calculate like that. Next important passive electronic component after resistor is the capacitor, which can be used to store electrical energy. There are various types of capacitors available in the market, like electrolytic capacitors with a thin layer of electrolyte connected to metal plates, capacitors using paper as dielectric, capacitors with air as dielectric, and ceramic capacitors. Each one is for a different purpose. There are also capacitors in which the capacitance can be varied, known as variable capacitors, often used in tuning resonant circuits. Capacitance is measured in farads, microfarads, nanofarads, or picofarads, depending on the value from higher to lower. High capacitance in circuits for smoothing out ripples in rectified direct current uses several thousand microfarads. Farad being a large unit is seldom used. A typical tuning capacitor in radios may be rated at 500 picofarads, 500 pf. A capacitor is said to have a capacitance of 1 farad if it can store 1 coulomb charge at a potential difference of 1 volt. There are few symbols associated with capacitors. This symbol 2 lines is for a fixed value capacitor, like the ones which I have shown. And this is a polarized capacitor. Electrolytic capacitors have positive and negative poles which have to be connected according to that in the circuit, while ceramic and paper capacitors or air capacitors do not need that. And this is the symbol for a variable capacitance, mostly used in tuning, and sometimes there are presets also. You can use a screw to change the capacitance and then fix it like that. It will not be a tuning knob. in some of the preset capacitors. They are usually smaller ones also. You may need to combine two capacitors to increase the capacity. When two capacitors are connected in parallel, the total capacity will be sum of the two capacities. Suppose you combine 2000 microfarad capacitors in parallel, then it will be acting as a 2000 microfarad capacitor. If you combine in series, the capacity will be lower. While capacitors are combined in parallel to obtain higher value of capacitance as in filtering circuits, series connection is to achieve higher working voltage, though the resultant capacitance will be lower. As in the case of resistors, inverse of the capacitances have to be added and the inverse of the sum obtained to get the resultant value of capacitance. The equivalent capacitance will be less than that of any of its components. These are a few electrolytic capacitors which I fished out from my recycle bin, or rather electronic junk box recently. The focus will be on this bigger one. You can see that this has a higher capacity rated at 1000 microfarad. The working voltage is given as 50 volts. And you can see that there is a minus sign here. That means this particular lead is for negative electrode and this one is positive. Another way of finding out is by the usual notation. The positive one will be longer. This is followed for most of the electronic components like diodes. Filter capacitors are used to smooth out the ripples in rectified DC. That is, when you use a diode, rectifier diode to rectify AC to DC, there will be ripples. Ripples in a rectified current can be smoothened by using high value capacitors like this. This is 1000 microfarad. You can use 2000 also, and multiple capacitors in parallel as well to smooth out the ripples in rectified current. Electrolytic capacitors have one plate as an aluminum or tantalum plate with an oxide dielectric layer. Second plate for an electrolytic capacitor is a thin layer of electrolyte which is connected to the circuit by another foil plate. Though electrolytic capacitors have very high capacitance, they have poor tolerance, high instability, gradual loss of capacitance, especially with high ambient temperature, and high leakage current. Electrolyte leakage from poor quality capacitors could damage the printed circuit board as well. There could be self-degradation if left unused for a long period, like a year, and might lead to short circuit when full power is applied. At high strengths of electric field above the nominal working voltage of the capacitor, the dielectric separating the two plates of the capacitor might become conductive. This is known as breakdown voltage of the capacitor. Maximum energy which can be stored in a capacitor is limited by the breakdown voltage. The air gap between plates of capacitors used in high voltage vacuum tube circuits need higher spacing to prevent arcing. Capacitors with mica as dielectric between the capacitor plates have much higher breakdown voltages than air capacitors. Ratings of capacitors in general applications may range from few volts to kilovolts. Dielectric has to be thicker for higher voltage rated capacitors, making them larger. When a capacitor is connected to a circuit with direct current supply, it will allow current to flow till it becomes fully charged, usually a fraction of a second, depending on the capacity of the capacitor. Once fully charged, dielectric does not allow further flow of current through the circuit. Initial flow of current is only to charge the capacitor plates and not through the dielectric when the voltage applied is below the breakdown voltage. Beyond the breakdown voltage, the capacitor gets damaged and may produce short circuit. When an alternating current is applied to a capacitor, as it changes polarity with a fixed frequency, the capacitor keeps on charging and discharging. Here the current continues to flow through the circuit, though electrons do not cross the dielectric material of the capacitor. In effect, a capacitor blocks DC while it allows AC to flow. Higher area of the capacitor plates increases the capacitance. In other words, capacitance is directly proportional to the area of plates. Relation between the spacing and capacitance is the other way around. Closer the plates, higher the capacity of the plates to hold charges, because electrostatic pull on the electrons collected at the negative side of the voltage source will be more. So, capacitance is inversely proportional to the spacing between the plates. But too close plates will cause arcing at high voltages. Dielectric constant of the material between the plates is also important. Compared to vacuum, air has a dielectric constant of 1.0006, while mica has a dielectric constant ranging from 5 to 9. Higher the dielectric constant, higher the capacitance. This picture illustrates different types of capacitors. From left to right, they are multi-layer ceramic capacitor, ceramic disc, multi-layer polyester film capacitor, tubular ceramic capacitor, polystyrene capacitor, metallized polyester film capacitor, and aluminum electrolytic capacitor. An inductor is simply a coil or loop of wire which opposes a change in the current within it. Inductance of a coil is measured in Henry. Inductance of a coil will depend on the number of turns in the coil, permeability of the medium inside the coil, cross-section of the core, and the spacing between the turns of the coil. The more number of turns there are in the coil, higher the inductance. Higher permeability of the core also increases inductance. Coils with larger cross-section have higher inductance. In the case of spacing between the turns of the coil, it is the other way around. Smaller the spacing between the turns of the coil, higher the inductance. The inductance in this discussion is actually self-inductance of the coil. A change in the current in the coil induces a voltage within it. 1 Henry is the amount of inductance required for generating 1 volt of induced voltage in the coil when the current is changing at the rate of 1 ampere per second. As in case of capacitance, smaller units are millihenry and microhenry. Just as the change of current in a coil can induce a voltage in it, the change in current with corresponding change in magnetic flux can induce a voltage in a coupled coil which is very near to it or wound over it. That is known as mutual inductance and forms the basis of transformers. This applies only to alternating current which changes continuously. In case of direct current, change occurs only during the moment the circuit is switched on. So practically there is very little opposition to a direct current by an inductor except the minimal resistance of the wire. But when an alternating current is applied to the same coil, there is significant impedance to current flow depending on the frequency of the alternating current, which is higher at higher frequencies than at the usual 50 Hz of the supply voltage. Diagram illustrates a transformer with two windings on a core. Usually laminated cores are used for transformers. Here primary winding has NP turns. The primary current is IP. Primary voltage is VP. Secondary winding has NS turns. Secondary current is IS and secondary voltage is Vs. The ratio between the turns of primary winding and secondary winding will determine the change in voltages between the two windings. Here you can see that primary winding has more number of turns than the secondary winding. So this will act as a step down transformer. It will decrease the voltage which is given to the primary winding as a lower voltage in secondary winding. You can see that primary winding is made of thinner wire in this case and secondary winding is made of thicker wire. That is because primary winding with more number of turns will have higher inductance and hence the current in the primary winding will be lesser than the current in the secondary winding in case of a step down transformer. If you want to step up the voltage, it will be connected the other way around. If a lower voltage is given to the secondary winding of this transformer, you will get a higher voltage in the primary winding. But actually, if you connect that way, you cannot call it as primary and secondary. The nomenclature will also have to be reversed. So in a step-up transformer, primary winding will have lower number of turns and secondary winding will have higher number of turns. The ratio of the voltages is having the same value as the ratio of the number of turns. This is a transformer which I can use for the power supply. This is secondary output. You can see two wires going. That will be 12 volts. And this is the primary connection to the mains supply. The turns ratio will decide the voltage in the output. Suppose this is 230 volt and this is 12 volt output. That's a step down transformer and you need a turns ratio of 230 to 12 to get a step down transformer. The number of turns will be much higher than 230 because you have to cover the current needed and sufficient impedance to the alternating current should be there. So the number of turns will be much higher, and on the higher voltage side, as the current is lower and the voltage is higher, you will use thinner insulated copper wire, and on the secondary side, as the current will be more and voltage will be lower, you use a thicker insulated copper wire. That is the usual pattern in step down transformers. I have just removed part of the cover of the transformer just to show the laminated core. You can see that this core is made of several laminated sheets, and the lamination is needed to prevent eddy currents. The core will have eddy currents, will heat up the core, and that can be prevented by using a laminated core. And when eddy currents are there, that will cause generation of heat and loss of energy, so that the efficiency of the transformer in converting the power will be reduced if you use core without lamination. Core with lamination will improve the efficiency of the transformer. I have used a pair of crocodile clips to connect the secondary winding of the transformer to the multimeter. You can see one connection here. This is one connection, and the other connection is here. I have used different colors of wire just for convenience. This is a black wire to one part of the secondary winding. This is a yellow wire, and these will go into the multimeter. One connection is here, another connection is here. So it is displaying a voltage of 10.5 volts. Minimal fluctuation is there. That could be due to fluctuation in the line voltage input. You can see that I have selected at 200 volt range. There are two ranges in this multimeter, 750 and 200. At such a higher range, there could be some error also. Anyway, 10.6 is the approximate output voltage of the transformer at the moment. This will vary depending on the power supply, because AC power supply, there could be fluctuation in voltage which could cause a change in the secondary voltage as well. An inductor is also called a choke because it tends to choke the flow of a fluctuating current through it. This property is used in the process of filtering a rectified direct current along with high value capacitors. As the inductance opposes changes in the current, it smooths out the ripples in a rectified DC. But they are not as commonly used as filter capacitors in rectifier circuits, as the inductance needed will make the quite bulky at the low frequency of 50 Hz. At higher frequencies, as the effect is much more, inductors can be used. An important use of an inductor in amateur radio is a common mode choke in feed lines to prevent something known as common mode current, which has been covered in another video on this channel. We discussed about conductors and insulators earlier. There is another group known as semiconductors like germanium and silicon, which are bad conductors of electricity in their natural form. If some impurities like boron or antimony are added in minute quantities to these, they can have either an increase in free electrons or a deficiency of electrons. Then they become semiconductors. The process of adding impurities is known as doping. When there is a deficit of electron, it is called a p-type semiconductor. They have positively charged holes as charge carriers. N-type semiconductors, on the other hand, have excess electrons as charge carriers. Silicon has 4 electrons in the outermost shell. When it is doped with boron, having only 3 electrons in outer shell, it becomes a p-type semiconductor with deficit of electrons or holes. Doping with antimony, which has 5 electrons in the outer shell, makes it an N-type semiconductor with an excess of electrons. P-N junction is constituted by a combination of p-type and n-type semiconductors in a diode. Current flows across the junction only when the positive pole of the battery or voltage source is connected to the p-type semiconductor. This situation is known as forward bias. Positively charged holes are repelled by the positive terminal of the battery. Similarly, electrons are repelled by the negative terminal of the battery. They cross the junction and combine with each other. For this crossing to occur, there should be at least 0.7 volt for silicon junctions and 0.3 volt for germanium junctions. At lower voltages, there is a depletion zone of carriers at the junction. This causes a current to flow across the PN junction when it is forward biased. In the reverse bias situation, no current flows across the PN junction. That is how a semiconductor diode functions as a rectifier, converting alternate current into pulsating direct current as it cuts off one half of the AC. A diode is composed of a PN junction with P-type semiconductor on one side and N-type semiconductor on the other side. That is the PN junction. Then we have to know that when it is forward biased, there will be a depletion zone here where the current carriers will be minimal. And forward bias means P-type is anode that is connected to the positive pole of the battery, and cathode or the N-type is connected to the negative pole of the battery. This is the electronic symbol corresponding to the diode. Then this is the blown out picture of the diode. You can see that there is a ring at one end, or either a marker, which you can see here also, but this is a real diode. The marker is very tiny. If you are careful, you can see, or with when you see it directly, you can see very well. This is a rectifier diode, and this will be the cathode, and this will be the anode of the diode. So this basic information is needed. And when a diode is forward biased, these are silicon diodes. When silicon diodes are forward biased, there will be a voltage across, that is 0.7 volt. Usually for silicon diode, it will be 0.7 volt, and for germanium diodes, which are seldom seen nowadays, it will be 0.3 volts. So this is what we are going to measure using a multimeter in the mode for diode testing mode. There is a selector switch which will select for diode testing. We have to know about the concept of peak inverse voltage, that is the maximum voltage which the diode will withstand in reverse bias condition. Usual diodes will withstand about 50 volt in reverse bias condition, but there are high voltage diodes also which can withstand very high voltages. So that is peak inverse voltage. When you apply an alternating current to the diode for rectification, you know that during one half of the alternating current, the diode will be forward biased, and during the other half of the alternating current cycle, it will be reverse biased. So that is where this peak inverse voltage comes in. If the peak inverse voltage is low and you are applying a higher voltage of alternating current to the diode, then it will break down. For testing a diode, you have to choose the selector switch in such a way that it indicates the diode symbol. That is how you test it. And then the black lead is connected to the cathode and the red lead is connected to the anode. Here I am using a yellow cable with crocodile clips on either sides to connect from the red lead to the anode. And you can see the display here 555. That is actually 0.555 volts or 555 millivolts that is being shown here. Now we will reverse the connection and see. Now the connection of the diode has been reversed, and you can see that what is shown is 1. 1 in this multimeter means it is beyond the range. It is not measuring that. So that is because this is reverse biased now. When the diode is reverse biased, no current flows across the diode till it reaches the breakdown voltage or peak inverse voltage, which we discussed in the beginning. Now I am testing another diode of the same type. You can see that there is slight difference in the voltage across the diode in forward bias condition. It is 538 millivolt rather than 555. This was the diode which we tested initially, and this is another diode. There is slight difference. Such variation can occur from device to device. Transistor is a semiconductor device invented by John Bardeen, Walter Brattain, and William Shockley in 1947, and they received the Nobel Prize in Physics for this invention in 1956. It is a device used to amplify and switch electrical signals. Large number of transistors can be included in a single chip known as an integrated circuit, which are the building blocks of modern computers and many other solid-state devices. Most of the transistors are currently made from silicon, while germanium was used earlier. Field effect transistors have only one kind of charge carrier, while bipolar junction transistors may have two kinds of charge carriers. In comparison to vacuum tubes, transistors are much smaller and require less power, often working at much lower voltages. Currently, two basic types of transistors in use are the field effect transistor (FET) and bipolar junction transistor (BJT). Terminals of the FET are named as gate, source and drain. Voltage given to the gate can control the current between source and drain in case of FET. Terminals of BJT are named base, collector and emitter. Current at the base terminal, which flows between the base and emitter, can control or switch a much larger current between the collector and emitter. That is how BJTs are used for amplification and switching. BJTs are generally grouped into two, NPN and PNP, depending on the types of semiconductors in them. N-type semiconductor has excess of electrons, while P-type semiconductor has a deficit of electrons or holes, which are considered as positive charge carriers and hence the name. These two types are made by mixing small amounts of other materials into the silicon chip by a process known as doping. There is difference in the amount of doping between various layers of NPN and PNP transistors. Emitter is heavily doped compared to other two layers. Collector is typically doped 10 times lighter than the base. FET is also sometimes called a unipolar transistor, as they have only a single type of charge carriers. They can be N-channel or P-channel depending on the type of semiconductor used. They are named as field effect transistors as they use an electric field to control the current. Two types of FETs are the junction FET or JFET and metal oxide semiconductor FET or MOSFET. Voltage applied to the gate terminal controls the conductivity between the drain and source. Though Julius Edgar Lilienfeld proposed the concept of a field effect transistor in 1925, a working prototype could not be made then and had to wait for further development of semiconductor technology. Three main types of configurations in which transistors are used are the common emitter, common base and common collector. While two leads each are needed for input and output of an amplifier circuit, the transistor has only three. So one lead has to be common between input and output. The transistor configurations are named after the lead which is common to both input and output in the given configuration. In actual circuits, there will be resistors and capacitors in addition. Radio frequency circuits will have inductors and transformers as well. Values of each component will be calculated according to the purpose of the circuit. In all these configurations, the emitter is forward biased and the collector reverse biased. Most common type is common emitter configuration, in which emitter is grounded, base acts as the input and collector as the output. So the input is given between the base and the emitter, which is grounded. Current gain in this configuration, which is the ratio of collector current to the base current, is known as beta or HFE, which stands for hybrid parameter forward current gain common emitter. Beta is always more than 1. This configuration has medium input and output impedance levels. Both current and voltage gains are medium. There is a 180-degree phase change between input and output, so that output is the inverse of the input. In common base configuration, emitter is the input terminal and collector is the output terminal, while base is the common terminal. This configuration is also known as grounded base configuration. Alpha is the current gain in common base configuration. It is the ratio of collector current to emitter current. Alpha is always less than 1. When there is no AC input, the alpha is known as DC alpha. Low input impedance and high output impedance are features of common base configuration. Voltage gain is high, but current gain and overall power gain is low compared to other configurations. The input and output signals are in phase in common base configuration. Low input impedance can provide a good match to 50 ohms, which may be useful in RF linear amplifiers. Grounding of the base can also reduce unwanted feedback between input and output stages in RF circuits. Base is the input terminal in common collector configuration, also known as grounded collector configuration and emitter follower. It is called emitter follower because the emitter voltage follows that of the base, though the emitter voltage is lower by an amount equal to the turn-on voltage of the base emitter junction. Here output terminal is the emitter. Gamma is the current gain in common collector circuit. Though the current gain in this configuration is high, voltage gain is unity. Input and output signals are in phase. Emitter follower configuration has high input impedance and low output impedance. High input impedance is useful in preventing loading of the previous stage. Thus, it is an ideal buffer amplifier. Current gain or amplification occurs in transistors between the base and collector currents with common emitter configuration. It is technically termed as HFE, which stands for hybrid parameter forward current gain common emitter. Another term is beta of the transistor. It is measured by dividing the collector current by the base current in a common emitter configuration. Most digital multimeters have an option to check the HFE of transistors. The transistor has to be inserted in the NPN or PNP slots according to the pinout diagram, and the selector knob turned to the HFE option to read the value on the digital display. Here you can see that BC547B, which is an NPN transistor, has been inserted in the socket for NPN transistors, and the selector knob has been turned to HFE on the dial. Digital display shows HFE value is 256, which is the current gain of this device as measured by the digital multimeter.